Hello, welcome back. Today I'd like to share with you the most useless skill that I personally have. And along the way, I want to talk a little bit about inertia and Newton's laws of motion with a practical demo that I'll do for you here. So my useless skill is that I can take these coins, any coin, you know, quarters, pennies, whatever, put them on my elbow and then snatch it from thin air. You know, just kind of like grab, kind of like move really rapidly and just grab it like that. Now I've done up to maybe 6 or 7 coins, over the years when I was a kid, but I'm going to try to go for my personal record here, see how high I can go. I think I could probably get to 20, 25, maybe 30 coins. We'll see. I don't know. We're going to see how far I can get. So if you're going to try this out, I recommend that you start with a quarter because it's nice and big and you can see it. And so what I'd like you to do is just put your elbow, try to keep it as level as you can. You're going to have to kind of tilt it up so that the back part here is level. Take the quarter, put it on near the edge, not the very edge, but right around here, and visualize your hand snatching through the position in space where that quarter is. And I have read about, sports people visualizing taking shots, visualizing archers shooting the bullseye, visualizing golfers. People do that mental imaging. I thought it was always, not true, but actually it is. You need to practice your mental imaging of bringing your hand through there. All right, so in order to go anywhere with this beyond 1 or 2 of these things, you're going to need to learn how to spread them out. So what I'd like you to do next is take 2 coins like this there, and what you need to do is visualize yourself hitting and intersecting both of them like this. 1, 2, 3, and there you go. All right, so let's double that. Let's see if we can get all the way to 4. And the way that you need to practice 4 of them is to spread them out in a line, as straight of a line as you can, and visualize intersecting that line. 1, 2, 3, there you go. And you can see that I caught all 4 of them there. Now I want you to notice that the moment I drop my elbow, all of the coins remain motionless in space for a split second. This is inertia in action, Newton's first law of motion. We'll be talking a whole lot more about this as we drop more coins. Now, I do need to tell you, there is a little bit of a trick to this. Whenever you bring your hand to grab it, you see if I don't do anything, then what happens is as my hand grabs it, the coins go right through the circle of my hand here. If you just go straight ahead, that's not going to help you. Whenever you do it, you have to rotate your hand so the palm is what actually grabs it. So in the same motion of going forward, you're bringing your palm into position so that it's hitting the palm of your hand. That's very important, otherwise you can't do anything. So that was 4 coins. Now I've done that before, so I knew that it was possible for me to do that. In order for you to make any progress going any farther than this, what you need to do is you have to get good with stacks of coins. So what I'm going to do is start here with the 10 coins right at the end and go 1, 2, 3, and then here they are in the palm of the hand. Okay, just like that. Now, the process from here on out is very straightforward. You make multiple stacks and just get as high as you can. Now, I know I could do 10. Maybe I can get to 20. I haven't really tried beyond that. You're going to start making mistakes. It just takes practice. Before we go any farther, let's talk about a little bit about what's going on here. And then, of course, we'll do a lot more detailed discussion at the end, right? What's happening here is every body in the universe that has mass, right, which means it's composed of atoms of some kind, some atoms, the copper atoms in here, nickel, whatever, they have what we call inertia. Inertia is a property of all matter. You have inertia, the coins have inertia, the earth has inertia, everything that has physical matter has this concept called inertia. Newton's first law of motion that you might have heard says an object at rest tends to stay at rest, but an object in motion tends to stay in motion unless it's acted upon by an outside force. Now, the word inertia doesn't appear in those sentences, but it's basically a law of inertia. What it's saying is that if an object has mass or is made of matter, then the more matter it has, the more number of grams of mass in there, the higher the amount of inertia it has. And the fewer the grams, the fewer the number of atoms or the size of the atoms, means the less inertia it has. And this concept of inertia is the resistance that the object has to changing its state of motion. You know, whenever I draw my elbow out from underneath, you can see for a split second, the coins are basically motionless. Yes, of course, gravity begins to accelerate them down, but in that split second, they're resisting the force of gravity. There is some intrinsic property to matter that causes it to resist motion or forces acting on it is what I'm trying to say. Now, eventually, the forces do begin to get it to move, and that ties into Newton's second law of motion we'll talk about in just a minute. But at the very instant of moving, they tend to stay where they are. That's what it means. An object at rest tends to stay at rest, unless acted upon by an outside force, in this case, gravity. And an object moving in a straight line will also continue to move in a straight line, again, unless it's acted upon by some outside force, like, you know, gravity or electromagnetic force or friction or something like this. So when you look at these in the further times that I do this, I want you to pay special attention to the moment I draw my elbow down and see how all of the coins independently and individually exhibit their inertia by resisting the force of gravity to cause it to change its motion. Eventually, gravity is able to do its job, but it is not an instantaneous thing. It takes some time for that to happen. So here you go. I can do one big fat stack, but it gets difficult to balance it. So what I am going to do instead is make two stacks like this. All right, 1, 2, 3, and there we go. Caught them all. Oh, drop one when I open my hands, but I still count that because I caught them all. So there's 20, so that's my personal record. I know I can do 20. Let's try for 30. Now I can say right now that the hardest part of this is actually stacking the coins. So here's 30 coins, and it's pretty difficult to get it to stand in one tower. I could grab this if I could, but any microscopic movements is going to make it difficult. So how do you actually do this? I recommend you put it in the palm of your hand like this, have them all lined up, and then you're going to have to somehow put them on your elbow. Or you could have another person help you, but I don't think another person is going to be super helpful. So here's 30 coins. I'm going to try 3 different stacks. This is why I told you practicing in a straight line was important. Okay, here we go. 30 coins. 1, 2, 3. Whoa, there we go. Caught them. Okay, so I didn't know that was going to work. There you go. I did a bunch of slow motion takes here. Here's 20 coins, 4 stacks of 5. And again, it takes practice to visualize your hand cutting through all of the stacks before grasping it. Now here's a take of 30 coins, but actually when I count them, it's 31. I want you to notice in great detail when I pull my elbow down, how the coins at the end of the elbow begin to fall first, followed by the ones closer to my head. Basically, the coins nearest the elbow are actually released first, so they fall first. Now this is as high as I got. This is 50 coins, and first I tried it into 3 stacks. And you can just see that when I released my elbow, everything for a moment remains motionless. Then gravity takes over, and you can see the acceleration as it begins moving faster and faster as the frame goes on. And for this take, I remembered to actually show the camera all the coins so everybody knows I caught them. Here's another take, again with 50 coins, trying it in a stack of 2, which worked pretty well. You know, when I worked at NASA, people always ask me, where's the anti-gravity chamber? Really, the only way on Earth to have any anti-gravity, if you want to call it that, is free fall motion. So you can see when I release my elbow, all of the coins are effectively all accelerating down at the same rate, and so they all, in their own frame of reference, appear weightless and spinning around as you would sort of see them if they were in a spacecraft in orbit. Kind of funny in slow motion, you can see the skin on my face kind of go back and forth, rippling with like waves through my skin there. And you might be wondering, why am I wearing the glasses? It's because I have 900 watts of bright lights in my face for slow motion. And I have to say, the absolute hardest part of this whole thing is trying to stack these coins on the elbow. You don't know how many dozens of times they just kept falling and falling and falling and falling, and you have to reset. So I wanted to at least show you one time of the outtakes of trying to do this stuff. So what I'd like to do instead is talk in a little more detail about what's really going on here. It's a simple looking thing, right? But it demonstrates something, especially in slow motion, that's pretty profound. You see, in the olden days, before Newton, and the scientists and the philosophers really that were there before Isaac Newton, Isaac Newton's law says an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an outside force. That phrasing is and was revolutionary. Because before that point, everyone thought, the scientists of the day thought, that you had to continuously provide a force in order to move an object. Like if I have this, let's take this quarter here. If I put it on my hand, then the only way to get this thing to move is to push it, right? But notice when I stop pushing it, it stops moving. And then I keep pushing it and it keeps moving. So the way scientists and philosophers thought for hundreds of years was that in order to keep something moving, you have to keep pushing it, right? And then Newton started to figure out, well, wait a minute, that's not quite right. The only reason it's stopping is because of another force that we call friction between the coin and my hand. That's the reason why it's stopping. If you take away the friction, for instance, if you do the same thing on an air hockey table or on a very, very smooth ice, then yes, eventually it will slow down, but it'll go much, much, much farther. And now we know, because we have spacecraft, that if we go into space where there's no friction at all, it really will go forever and ever without stopping. So the mode of thinking before Newton was that in order to keep things moving, you have to keep pushing them. But then Newton said, no, 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 no. Actually, every object in the universe is either going to be at rest and it'll stay that way forever. In other words, I can put it on my hand and it will stay on my hand forever unless something comes and a force moves it. And if I get this thing moving, either in space or on a very frictionless surface, it will keep moving forever and ever unless some other force acts to stop it. It just so happens that we're always surrounded by friction, either air friction, or if you're in the water, water friction, or on the surface of any object, real object, friction between two contact points between objects, right? And so we're always being slowed down. And so it kind of fools us, or it fooled us for a long time. But Newton said an object in rest will tend to stay in rest, and an object in motion will tend to stay in motion unless acted upon by an outside force. And the outside force can be anything from friction to electromagnetism to electric fields, magnetic fields, gravitational fields, any of the forces in nature. Right? Most of the forces that you feel in everyday nature are actually electric forces and magnetic forces. Even friction, when you get down to it, the electron clouds that are separating things, those are electrical forces that are repelling each other. And that's the cause of the microscopic cause of friction there. Right? But that is Newton's first law in a nutshell. And it was a paradigm shift because now we know that the natural state of motion is to be moving at a constant velocity. And that constant velocity could be rest. Notice that object at rest tends to stay in rest. An object at rest just means it's moving with zero velocity. So really the law says that objects are always moving. And they're not going to change their state of motion unless some other force acts on it. So whenever we remove the elbow, then it is going to stay in its previous state of motion at rest, unless acted upon by, in this case, gravity, which then slowly begins to pull it down. And that's what you see in slow motion. Now, we could talk for hours about inertia, honestly, because, these are just laws that we use to observe what this stuff is, how it behaves. But then you have to ask the question, microscopically, what causes inertia? What is it about matter that causes it to resist forces, basically to keep going in a straight line unless acted upon by a force? And even when you push it, the more mass it has, the more resistance it'll have. A bowling ball will have, once it's moving, a greater resistance to moving, changing its course than a ping pong ball, for instance. We all know this. More mass means harder to get moving, right? That's called inertia. Where does it come from? Well, we're still working on those things, but the current theories is something called the Higgs field. Basically, matter is a type of energy field, when you really get down into it, that interacts with something called the Higgs field, and that gives rise to the concept of inertia. But then you could go deeper and say, well, what's the Higgs field? Eventually, you get all the way down to quantum mechanics, and then you don't have any answers for anything, because we are composed of quantum objects called atoms, and we're just observing the way things are around us. But to really be outside of the system and really understand the why or how it could be otherwise, we have no capability to do that. So my advice is to go down to a level that you are intellectually satisfied, and beyond that, you start getting into, well, why does the Higgs field exist? Why do energy fields exist? Then you start to get into questions that we just have no ability to answer. All right, so what I'd like to do now that we talked a little bit about inertia in the demo here is dive a little bit more deeply into Newton's first law and second law and third law of motion. Quick recap, the first law is the law of inertia. Object at rest tends to stay at rest. Object in motion tends to stay in motion unless acted upon by an outside force. That's the first law of motion. Second law of motion is summarized by forces acting on an object is equal to the mass of the object times the acceleration. It connects the concept of a force to the change in velocity, the acceleration. So it's very much tied to the first motion, but it's mathematical. It says if I push on an object with a certain force, how will it move? That's basically the second law. And the third law is the famous action-reaction law. Every action has an equal and opposite reaction. So and that has to do with forces. So if I push on an object, the object will literally be pushing back on my hand or wherever I'm contacting with an equal and opposite force, because when you have a force between two objects, it always involves two objects. So you cannot be pushing on one object without it pushing back. Now I know what you might be thinking, well, if I push on a wall, how is the wall pushing back on me? That doesn't even make sense. It doesn't have hands. Well, it's the electrical forces and the springiness, the elastic forces and the springiness of the atoms. When you try to deform a solid or a wood or anything like this, it's going to tend to be pushing back. It has a springiness to it. So when I push on the wood, it's pushing back. But this action-reaction occurs between any two objects, even the exhaust from a rocket engine and the rocket itself. So when I push the exhaust out the back, the exhaust pushes the rocket the other way. So action-reaction goes into all types of locomotion. Even walking is an action-reaction force between I'm pushing on the ground sideways and the ground is pushing on my foot. You just have to get over the idea of what does it mean to push back? It's just the electrical forces basically at the microscopic level that has been kind of deformed and is springing back and exerting a force back. That's basically it. All right, so let's dive a little bit deeper into these laws of motion and then wrap it up. Objects at rest will stay at rest unless they're acted upon by an outside force. That's sentence number one. Objects that are in motion will continue to stay in motion in a straight line unless acted upon by an outside force. So let's break this down. An object at rest, what does that mean? Right, so I can have a crate here, and I can say it's at rest. And when I say it's at rest, this is the ground. Okay, so we just walk up in the forest and you find a crate or some box or something, an apple, sitting on the ground. It's not moving. You stand there and you look at it. All right, what Newton's law is saying is that that object, when it is initially at rest, it's going to stay at rest unless some force comes along and pushes it. That's very simple to understand, okay? But sometimes the simplest things are the most core fundamental things that we have to have in our brain. So what would cause that apple or that crate or whatever it is in the forest to actually move? Well, the wind could come and blow it. That would be a force. That would be moving it from its initial place at rest. All right? It could be an earthquake shaking the ground. That would be a force. That would cause it to move. I could go over and I could kick it. That's a force. You get the idea. A squirrel could come along and start eating it and rolling it around. Those are forces. So if you literally never exerted a force on that object that was at rest, it would literally stay at rest forever. It would never move. Right? So an object at rest tends to stay at rest. That just means it won't move unless acted upon by an outside force. Right? That's sentence number one. Now, I could go into deep space and I could have some kind of cannonball or something like that, and I could shoot this thing, out of this cannonball, right? Like this. And this thing is traveling with some velocity v. It's going to the right. Now, if we go in deep space, why am I choosing deep space? Because there's no forces, there's no wind, there's no earthquakes, there's no birds, there's no people, and there's no gravity either if we're in deep space. I'm talking about outside of our galaxy, okay? You happen to float your spaceship up and you notice that there's this object traveling through deep space. It's traveling with some constant velocity and it's going in a straight line. That object will continue to go in a straight line forever unless acted upon by an outside force. You could literally cruise right next to this thing and just watch it traveling with it for thousands and thousands and thousands and millions and billions of years, and it will never move unless it's acted upon by an outside force. What kind of force could act on that thing? Well, I could bump it with my ship, right? If I bumped it with my ship, that would impart a force, and it would not be traveling in a straight line anymore, right? So an object in motion will tend to stay in motion unless acted upon by an outside force. I could shine a very high-powered laser on it. that would, we're getting into momentum here, but that would impart a little force which could push it and change its trajectory. But the idea is that objects are going to travel in a straight line unless acted upon by an outside force. Now, in our solar system, when we shoot a space probe, of course, the trajectory is always curved, but that's because the gravity from the sun is pulling on it, exerting a force. But when we're away from any forces, things always want to travel in a straight line. And here's the critical thing. When an object is traveling in that straight line, think about that cannonball in deep space. It's just cruising along, and I'm cruising right next to it, looking at it. And there is no force acting on that thing, but it is still traveling in a straight line. So in other words, forces are not required to maintain the state of motion. There is no force required to get that ball to continue moving. Once the object is moving, no forces are needed or necessary. The object just keeps moving forever. In our universe, things just keep moving. And if they're already still, they're still moving. It's just that they're moving with zero velocity. So it's really the same law, right? When you think about it, an object in rest tends to stay at rest. An object in motion tends to stay in motion unless acted upon by an outside force. So you could kind of boil the whole thing down just to say that objects always continue moving in a straight line unless acted upon by an outside force. It's just in the case of an object at rest, its velocity is zero. So of course it's going to maintain a zero velocity forever. And if its velocity over here is 15 meters per second, it's going to maintain a 15 meters per second velocity forever. No force is required to maintain the motion. You see, because in the early days, before Newton, people thought that forces were needed to maintain the motion, to keep the motion going. That's what people thought. Newton came along and said, no, no, no. Once the thing is moving, there are no forces necessary to keep it moving. Forces just tend to change the state of motion. All right? So that's why I'm going to write my first words on the board here. I'm going to put it in all capitals. Forces do not cause motion. And then under this, I will say forces cause objects motion to change. Triangle means change. So I'll put a little exclamation point right here. This is a critical distinction. All right. This is actually the main impetus, the main thrust, no pun intended, of Newton's first law of motion. Prior to Newton, people thought that objects that were moving, like on the Earth here, that forces were required to maintain their motion. Think about pulling a box on the ground, on the grass or on the carpet. I have to pull that box. As soon as I stop pulling, the box stops. And then I want to move it again, I got to pull it again. But as soon as I stop pulling, it stops. So that conditioned people to believe that when things move, you must be constantly maintaining some force. But we now know, and I'll draw a picture in a minute, that the reason it stops is because there's a force acting on the box called friction. That is why the box stopped. If there's no friction, then the box actually would keep moving on forever. Think about the case of an icy lake, a frozen lake. You grab a puck or something and you slide it just with one little push, you let go, you're not touching it anymore. Of course, it goes on and on with very low resistance to motion, very low friction, so it goes on and on and on. And if you reduce the friction all the way to zero, it goes forever and ever in a straight line, right? But in everyday situations, when we pull things or push things or whatever, they generally stop because there's almost always friction acting in the real life, but friction is a force. So the object tends to want to continue moving once we get it started, unless it's acted upon by an outside force. So forces do not cause motion. That just means that once the motion is going, we don't need a force to continue the motion. That's what that really means. Forces cause objects' motion to change, right? If the object's at rest, a force will change its state of motion from rest. It'll start it moving, right? If an object's already moving and I apply a force to it, it's going to speed it up or slow it down or change its direction. Either way, I'm changing its state of motion. So forces cause objects' motion to change. But what is a change in motion, right? What is a change in motion? This is another way, this sentence right here is another way of saying forces cause acceleration. right? Acceleration. That's what they do, because acceleration is a change in motion. That is the definition of what a change in motion is. I mean, what is acceleration? It's the change in the velocity divided by the change in the time. How many meters per second I go up or down over how many seconds. I'm speeding up or I'm slowing down. And also, we're going to learn that this change in velocity, it doesn't necessarily need to be speeding up or slowing down. A change in velocity also counts if you change directions. If you're going this way and now I'm moving this way, I have now changed my velocity also. So forces cause acceleration. That's what they do. They don't cause motion to happen, or they don't cause motion to be, they're not required to maintain motion. Forces simply, when they act on an object, change the state of motion of the object. They cause an acceleration. And that's kind of dovetailing into Newton's second law, where we write down that force and acceleration are related to each other. But right now, in words, forces cause acceleration. They cause the object's motion to change. All right? So let's go back to the picture that people, used to talk about when we did the thought experiments about this. And what we'll do is we'll put a crate on the ground like this, just on some grass or rocks or carpet or whatever. And you pull this way with some force like this. Well, if I pull it this way and let go, it stops. If I pull it this way again, let go, it stops. It appears in everyday situations that I need to continue pulling on the thing to get it to move. That's why people thought forces are required to maintain the motion. But now we know that what's actually happening here is the rubbing that's happening here we call friction. And so there's always a frictional force that's basically running counter. If I'm pulling this way, the frictional force is trying to oppose the motion. So you see, forces do not cause motion, even though it appears to happen here. What's really happening is I'm pulling, but you see, forces, objects in motion tend to stay in motion unless acted upon by an outside force. As soon as I stop pulling, the outside force of friction stops the block. That's why it stops. And that fooled everybody for a long, long, long time until Newton codified it into his first law of motion and said, no, no, no. When objects are moving, they continue moving with no forces on their own forever in a straight line. There must be a force to change that state of motion. In this case, the force that stops the motion is the frictional force. But if there was no frictional force, then you would literally, once you terminated this pulling force, the thing would move forever and ever, just like it slides across a lake, frozen lake, or in deep space. All right, so now we need to transition to talking about the second part of this, which is kind of basically related to what we've already said, which is called the word inertia. So I'm going to write that word down, inertia. All right, again, I'm not going to write a definition of inertia because you're never going to look it up. I'm going to tell you what inertia is. Inertia is the tendency or the propensity for an object to remain at rest or to stay in motion. Basically, inertia is the resistance to something changing its motion. Let's take two situations. First of all, let's go back into deep space. Let's do a thought experiment. We're in deep space. We're nowhere near any galaxy or anything. We're literally in the middle of nowhere. And there's two objects in front of you. The first object is a golf ball, little bitty ball about this big. Right next to it is another object that is a car, like an automobile. You pull it from Earth, it's floating, they're both floating in space. Which one has more inertia? Well, the car has more inertia. Inertia is the measurement of the resistance to motion, the resistance to change its motion. If I go up to that ball and push on it with some known force of, let's say, 1 Newton, it's going to fly away. And it's going to go in a straight line forever and ever, even after I'm not pushing it anymore. Newton's first law. But then I go to that car and I push it with 1 Newton. It's going to start moving, but it's going to resist my motion. Just think about being in a swimming pool when you're floating and you have, an adult try to push on them when they're floating. It's hard, but when you push a child, it's easy to move them around, right? This has nothing to do with gravity. There's no gravity anywhere. We're in the middle of nowhere, in between the galaxies, thousands and millions of light years away. But that golf ball, when I push with a 1 Newton force, is going to start moving rapidly. When I push on that automobile, the car, it's going to resist my motion, but it will start moving and eventually it will accelerate away. And then, of course, it'll coast forever and ever away, at some known speed away from me. So those two things have different amounts of inertia. And what we're going to learn, and what we're learning right now, is that basically mass gives rise to what we call inertia. If an object has more kilograms of mass, it has more inertia. That means it's going to be harder to get it to move, right? If it has fewer kilograms of mass, it's going to be easier to move. This has nothing to do with gravity. We are nowhere near a gravitational field. The intrinsic amount of matter inside of something tends to cause the object to resist its state of motion. If it's already at rest, it's going to be harder to get it to move if it has a lot of inertia. If it's already moving at a high rate of speed, it's going to be harder to change its motion, to get it to speed up or slow down if it has a high inertia, high mass, right? And so what is mass anyway? It boils down to protons in the nucleus of the atom, neutrons. They both have a relatively high mass. Electrons are very small mass, so electrons don't really contribute much to the mass of the object, but a little tiny bit. Protons and neutrons in the nucleus of the atom, that is most of the mass of an object. So if you have something made of lead, those lead atoms have more protons and neutrons, so it's a more massive object than something made of carbon, let's say. Less protons and neutrons, and so it's going to have less mass. All right? So when we say something has high inertia, we're just saying that it's harder to get it to start moving to change its state of motion, or if it's already moving, it's harder to deviate its motion, to change its direction, or to change its velocity. All right, the next thing we need to talk about is what we call the net vector force. It sounds complicated, but I promise it's really not. Let's take two situations. Here is my crate resting on the ground. It's at rest, which means the velocity is equal to 0. It's not moving at all, okay? And then let's take another situation right next to it. Again, we have maybe a second crate separate from the first, and it's sitting right here as well. All right? Initially at rest, here it is. No force is acting on the thing. It's going to stay at rest forever and ever and ever. Its velocity will be 0 meters per second because Newton's first law of motion says that the object at rest will tend to stay at rest unless acted upon by an outside force. So we expect it to stay at rest forever. Now, let's take that same situation over here, initially at rest, and let's apply a force to it. Now, if we apply a force in this direction, we'll call that F1, right? Then, of course, we expect the box to start moving. It's not going to be at rest anymore because we're applying a force, and of course, the force is going to tend to move the object. If we then remove the force, then the frictional force will slow this thing back down to rest again, okay? But instead of applying one force to only one side of the block, let's say it's initially at rest, and I apply two different forces to this block, both equal and opposite, and I'll call this force number 2. So I'm literally going to take this box and like squeeze it between my fingers. Just imagine. I mean, I could just take this little magnet right here. This thing is at rest right now, okay? Now, if I push it, of course, it's going to start moving, right? But what if I apply a force to both sides, equal and opposite? Okay, you see, if this force is bigger, then of course it still moves this way. If this force is bigger, then it's going to move this way. But if the forces are exactly the same, then the thing doesn't move at all. So what I'm trying to say is if the force number 1, the vector number 1, we call force, when we add it to the vector force number 2, if that equals 0, then it stays at rest. So I guess I wanted to point out, because the law of motion says an object at rest will tend to stay at rest unless acted upon by an outside force. And then a lot of people say, well, wait a minute, there's forces here. Why didn't it move? Well, it's because when we say acted upon by an outside force, what we're saying is if multiple forces are acting, it's the net force acting on the outside of the thing. If an object has a net force different than 0, then it will change its state of motion. So what we could do is rewrite Newton's law. We could take some creative license and we could say an object at rest will tend to stay at rest unless acted upon by a net force, a net external force. So if we have two forces, the net force here is 0. When you add these vectors, one is in one direction, one's in the other direction, they're negatives of each other, it's 0, so the thing stays at rest because the net force on the outside is 0. So it's not so much that there's a force on the outside, it's that there has to be a net force that is different than 0, then of course the thing won't be at rest anymore. So forces actually cause an object to change its motion. But what is a change in motion? A change in motion is an acceleration. So what we're saying is that forces cause acceleration. That's what we learned before. Forces cause acceleration. Newton's second law of motion it writes this down in a mathematical way. So let's talk about it. Newton's second law of motion. The first law of motion was more of like an object at rest tends to stay in rest, an object in motion tends to stay in motion unless you push on it with a force. Newton's second law is the following. The force that you apply to an object is a vector quantity, and it's equal to the mass of the object multiplied by the acceleration that the object has. F equals ma. Now I'm putting the vector arrowheads on top to remind you that the force is a vector, it has a direction, and the acceleration is also a vector, it has a direction. The mass of an object is just how many kilograms it has, so there's no vector associated with the mass, okay? Now before we actually talk about this, let's write down the units of this thing. Now the force that we're talking about is always measured in newtons. The mass of the object is always measured in kilograms, not grams, kilograms. And the acceleration is measured in meters per second squared, right? And that's very, very important. So whenever you are calculating something in terms of forces and accelerations and things like that, keep your accelerations in meters per second squared. Keep your masses in kilograms. If you have some other unit like grams, change them into kilograms. And when you do that, then the forces will always be in newtons, right? And remember, a newton, as we talked about before, is roughly the force that you will feel from an average apple. When you hold an apple in your hand, that's about a newton. It's pretty close to a quarter of a pound if you like using pounds, but of course I don't like using pounds, but some people need that in the beginning. It's about the force you feel in an earth gravity of an apple sitting in your hand, a typical medium apple. What does this equation mean? This means that if I know how much something is accelerating, I can measure its acceleration. And I know how much mass that object contains. By multiplying these two, it tells me how much force I must be pushing with to cause that acceleration. Because remember, things only accelerate when there's some sort of force somewhere. Only. I'll say it again. Things only accelerate. They don't accelerate for no reason. You have to have a force. Newton's first law says things want to move in a straight line at a constant velocity. That's no acceleration. If I go into deep space and throw something, it's going to go forever and ever and ever in a straight line with no force applied. No forces. It's just coasting, right? But if I want to accelerate that object, what Newton's second law is telling you, if I want to speed that thing up, I have to apply a force to it. And that force, which is a pushing force of the rocket engines, is going to be equal to whatever the mass of the object is multiplied by whatever acceleration I want to give it. If I want to speed that thing up, let's say 5 meters per second squared, that's the acceleration. Then I multiply by the mass and it tells me how many newtons my rocket thruster must push with. So what it does is it relates the pushing of things, or the pulling, the forces, with how does the object respond. Because remember, forces don't cause motion. Motion happens automatically in a straight line forever and ever. Forces cause the motion to change, which is what we call acceleration. Now, that is what you're going to get out of most lessons, most lectures, most books, you know, and I'm not trying to say that I'm like some brilliant person telling you stuff that other books won't have, but what I'm trying to do is I want to focus on what I think things that aren't emphasized as much, because anybody can take this equation and multiply two numbers together, and we could do our first problem like right now. But I want to go deeper, because I want you to understand a little subsurface, a little bit deeper layer as to what's happening here. All right? Force is equal to mass times acceleration. What it means is that in order to produce an acceleration on some mass, I must push with some force. Alternatively, if I apply a force to some object and I know its mass, then I can calculate the acceleration that will result from that force of pushing or pulling. All right? Now, the vectors that are on top of these things, this is what we call a vector equation. And what it means is that because they're vectors, remember, a vector is a number, a magnitude, and also a direction. And because the acceleration has a vector and the force has a vector, both sides of the equal sign, what it means is that the force must be in the same direction as the acceleration. That makes sense. If there's an object here in space and I push this direction, I expect it to accelerate in the same direction. The vector arrowheads mean that the force and the acceleration always, 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 always have to be in the same direction.
Always. That little nugget right there will save you a lot of time in many problems, because sometimes you're not sure which way the acceleration should go, but you'll have some forces, and then you remember, oh wait, Jason said the force and the acceleration, they always have to be in the same direction. Why? Because this is an equal sign. And that means that the multiplication has to equal to the number of newtons, sure, but the direction over here has to be the same as the direction here because this is a vector equation. So now we're growing up a little bit, right? In like 6th grade, you learn how to write an equation. You know, y equals 3x plus 4. That's just an equation with numbers. Put numbers in, and you have to have the same numbers on both sides. But now we're growing up a little bit. We're in physics. And now we have a vector equation. And that means that the numbers you multiply have to equal the force. But since it's a vector, the direction here has to be the direction of the force. That's what the vector arrowheads on both sides mean. Because when I first learned physics, I kind of ignored the vector arrowheads. I didn't even write them half the time because I didn't care. I just thought, well, I'm calculating the force. But it's very important to know that the force and the acceleration are lined up. So what does this mean? Let's take a couple of examples, because this is just a general equation. But now let's say that I give you a force which exists only in the x direction. Then what it means is it's equal to the mass times the acceleration, which happens in the x direction. So this is a component in the x direction of the Newton's second law. And we also now know that the force which is pushing in the y direction is equal to the mass times the acceleration that happens in the y direction. Now you see how we're starting to break it into components. We learned in the past that we can break forces into x and y components. Why? Because then we can treat the x component as its own equation, find the acceleration in the x direction. We can use the force that's in the y direction component and get the y version, or the y amount of the acceleration. So to draw a few pictures here, let's say we have some block with a mass m. And this is the x direction here. So let's say I push to the right in the x direction. This is now purely in the x direction. I push on some box of mass m, and it's going to produce some acceleration in the x direction. The force and the acceleration are in the same direction, right? What happens if I have a block and I push upward in the y direction? Well, what it's telling me is that the acceleration is the acceleration a sub y is going to happen in the y direction. So the force is equal to mass times acceleration exists in the y direction, and the force and the acceleration are lined up in the same direction. The force and the acceleration in the x direction are lined up in the same way. So if you now broaden yourself and say, well, what happens if I'm not pushing in the x or the y direction? Let's say I'm pushing on this corner at some angle, and now I'm not gonna put x or y here because it's just some vector, it's some oblique direction. It's not really purely in x or purely in y. But what you do know is that the force and the acceleration have to be lined up. So these two vectors are lined up in the same direction. When you read force is equal to mass times acceleration with vector arrowheads, it means the directions are the same too. Now, in real life, if I was pushing on this block with some force at some angle, I would break this force into a vertical and a horizontal component. And then I would calculate the vertical and the horizontal component of the acceleration, which would reproduce what is happening here. But still, I just want to show you the force and the acceleration in all of these cases are in the same direction. So now let me get a little philosophical and tell you some insights that you may or may not read in a book. You can see that force is equal to mass times acceleration. We now know that force and acceleration are both vectors. They're both in the same direction in all of our pictures, but the length of the arrows might be different because, of course, when I multiply these, I'm going to get a new number over here, and so the length of the arrow might be bigger or smaller for force, but the directions will be the same. So basically, the force is a vector arrow in one direction. The acceleration is a vector arrow in the same direction. The only difference between the two vectors, other than what they represent, is the length of the arrow. So what you can say is that the force in this equation and the acceleration in this equation, they're basically related to each other by a conversion factor. The conversion factor is what we call the mass of the object, right? So the mass here, it's telling us how much influence the force has to produce an acceleration. In other words, remember the concept of inertia. We said we go into deep space and we have a very massive object like a car, like an automobile. If we push on it with 1 Newton it's going to move, but it's not going to accelerate very much because it has a high inertia, right? So if I have a very high number here and I push with the same force, then I'm not going to get very much acceleration. If you think about dividing by m, if m is very big, I'm dividing by m, acceleration is very, very low. And if I go to a golf ball, which has a very low mass, and I push on it, it's going to accelerate rapidly. So the mass is the conversion factor. That's, if you think about a conversion factor, what I mean is, like, you know that there are 100 centimeters in a meter. It's a conversion factor. Meters and centimeters are sort of the same thing, but the 100 is a conversion factor to change one into the other. Or liters to milliliters. Or, I can pick any unit I want to. I can pick a unit of density if I want to. All right? But you're converting between one unit of measure and another. So instead of thinking of forces as like a totally different thing as accelerations, philosophically, you can think of force and acceleration being the same thing. They're both vectors. They're both pointed in the same direction. They just have a different scale factor, and that scale factor comes about because of the mass. The mass tells us how much influence that force has to produce a change in motion. I'll say that again. The mass is a conversion factor that converts from forces to accelerations. And it sort of behaves as a conversion factor that tells us how much influence the force actually has to produce motion. If I have a very high mass, then a force will not produce much motion. But if I have a very low mass, the force will produce a lot of, I say motion, a lot of acceleration. So that's a little philosophy, but I mean, it's basically what's going on here. These two things are the same direction. That's the critical thing. The mass behaves almost like a conversion factor. Now, it's very important for you to realize that when I say force is equal to mass times acceleration, it's really the net force acting on an object. So let's say, for instance, that I have a body with mass m, and I have lots of forces acting on it. So I have a force like acting right here, I have a force acting here, a force acting here, and like, I don't know, it could even be pulling, some force acting right there. Maybe some force acting right here. So you could do a couple of different things. You could apply each of these forces equal to mass and find out the resulting acceleration separately due to each of these forces. Then you would have all of these different acceleration vectors, and you would have to add the vectors vectorially, and you could get the answer. But what we actually do is we change the problem from all of these different acceleration forces acting on the object. What we really do is we find the vector sum of those forces. And let's just say in this problem, once we add all these vectors up, we do the head to tail and we draw and all that stuff, we figure out that really the force resolves to being something like this. So the sum, this is sigma here, the sum of the forces, or you could call it F sub net. We call it the net force. The net force is what happens when you add vectorially all of these forces together. It behaves as a single force acting here with this amount, right? Then the acceleration, of course, has to be in the same direction as whatever the net force is. So when we say force is equal to mass times acceleration, if we have multiple forces, we resolve it to a single force, and then, of course, it's equal to mass times acceleration. We get a single acceleration out of it. So the way you might see that written in a book is really that the sum of these forces is equal to the mass times acceleration. This is a better version of Newton's laws because what you do is you add up all the forces, and the resultant force, but you're adding them vectorially, the resultant force is what matters to produce the acceleration. Another way you might see it is you might see it as F net is equal to ma, right? The net force. So what I'm trying to say is when you have multiple forces acting, you resolve it to a single force, and that single force behaves equal to mass time, and you can produce that acceleration there. All right? Now, what does it actually mean graphically? I'll do a couple of different things. I'm going to draw some pictures. But what I'll use is my magnet here. Let's say I'm producing a force. This is kind of more like this going here. I'm pushing here. And as the thing starts moving, my force is still being applied. You can imagine it being like a rocket thruster attached to the object. So as I move it, I'm still pushing it. Then it goes faster and faster and faster. I'll go over here. Because the force is still in contact with the object, well, if I can hold it, it goes faster and faster and faster. Because as the thing is moving, the force is still being applied. As long as the force is being applied, the acceleration is still happening, right? So if I continue applying the force throughout the entire time, it's accelerating the whole time. But let's say that I accelerate a little ways, and then I just let go of the force, and then the thing is going to go coasting in a constant state of motion. So if you have a rocket thruster firing, I'm accelerating the whole time, but then when the rocket cuts off, I'm coasting at a constant velocity. And everything starts floating in deep space because I'm at a constant velocity, an inertial frame of motion. So the first thing you have to understand is we have to analyze a little more deeply what a force is anyway. And you have to recognize in the beginning, and this is something that's not really like brought into focus until a little later in physics, but you have to recognize that anytime you have a force, any force you can think of, it's always some sort of interaction between two objects. I challenge you to think and try to come up with a force that doesn't involve two objects, right? And you won't be able to do it because anytime we have a force, by definition, there always has to be two objects interacting with each other. Let me give you some examples. The Earth interacts gravitationally and pulls on the moon, but the moon has gravity also, and it interacts and pulls on the Earth. So you see, there's two objects involved in the forces that are going on there. When I push on this board, my hand is in contact with the board. I'm pushing on the board, but you see there's another body involved, the board itself. There's two bodies involved anytime there's a force. If I have a rope and I pull on a rope tied to a car or something, I'm pulling on the rope, but you see the rope is attached to my hand. There's always two objects anytime there's a force. Even electric and magnetic forces, where you have an electron over here and a proton here, and they're attracting each other. You see what's going on? There's two bodies. Anytime there's an attractive force or a repulsion force, there's always two bodies. So I challenge you, again, to try to think of any situation where there's forces going on and try to find one where there's only one body. You won't be able to do it. If I flap my arms, like this, well, one of the bodies is my hand and the other object is the air surrounding my hand. So the reason I'm setting the lesson up like this is because I want you to have it in your mind that anytime you interact with a force or that you can imagine a force, it always involves two bodies, always. So then when you recognize that, then you understand a little bit more why Newton's law of motion, third law of motion, makes sense. So I'm going to say it out loud, and then I'm going to draw a lot of examples on the board. I'm also going to write it on the board because this one's important enough we need to write it. And Newton's third law basically says the following: to every action force, there is an equal and opposite reaction force. Sounds simple, right? But why is there an equal and opposite reaction force? The main reason is because anytime you have a force, there's always two bodies involved. So you can't just have a one-sided force acting. Because there's always two bodies interacting, there's always going to be some force reacting backwards in the backwards direction on the other body. That is why Newton's law says that for every action there's an equal and opposite reaction, because for every force you can imagine, and I just gave you 5 examples, there's always two bodies. So that's the fundamental reason. And the other thing I'll say out loud, we will also write it on the board, is that these two forces, they occur in pairs, action and reaction, they never act on the same body. They always act on the two bodies that are present in the interaction. So for instance, my hand pushes on the board. That is a force from my hand into the board. But the board pushes back into my hand, and that force acts on my hand. So you see the first force is me acting on the board, and the other reaction force is the board pushing into my hand. Both of those forces, they act on different objects. The first force acts on the board, and the reaction force acts on my hand. They do not act on the same body. If you think you have an action-reaction pair that acts on the same body, you're wrong, because it can't by definition. These forces, the action and the reaction forces, they always happen between pair of objects that are interacting, and they always act on different bodies. So let's draw some pictures and get a lot of examples, and then I'll write Newton's third law on the board out as well, and so that you can, by the end of this, understand exactly what's going on. So here you get to experience my drawing skills, because here I'm going to draw a ball, right? So here we go, ball, like this. And then I'm going to draw a foot kicking this ball, and I'm a terrible artist. You all know this. So here is a foot, something like this. And it's kicking the ball. So it's not just sitting here. It's like wham, it hits the ball like this. So what happens at the instant of time that we're interested in? Well, what happens is there is a force, so just forget about the foot. The foot kicks it, but just forget about it. There is a force that acts on this ball. It goes this way. And you could call it F, but to talk about more specifically what's happening, this is the foot acting on the ball. And that's because I've drawn the arrow from the ball. Now, of course, the force comes from my foot, but ultimately it's impacting this thing, and the force that's acting on this thing is in this direction, and it's because of my foot acting on the ball. Now, what Newton's third law is saying is that at the moment of contact, you see, as we said from many, many examples, there's always two bodies interacting between when there's a force. You cannot come up with a situation where there's a force happening and only one body. You can't have just like a force acting on itself. It never happens. So in this case, the two bodies are the foot and the ball. So when I kick the ball, I impart a force from the foot onto the ball. But at that moment of contact, then there is also a reaction force. That is a force, I'll call it capital F, I'll put my little vectors on top here, which is the ball acting on the foot. This is an action-reaction pair, all right? Now, the first thing you're probably thinking is, well, I've never felt a ball kick my foot. That isn't real, but think about it for a second. Just imagine a little soccer ball that gives a little bit. And when you give it a nice swift kick, you probably have felt the compression of that ball. And if you kick it at just the right, you can't see my feet here, so just imagine this is my foot. As it kicks the ball, I'm sure you've had that situation where your foot has rebounded off of the ball. That is the force of that ball kind of kicking your foot back. You have a microscopic compression of that ball, which deforms the ball, and that increases the pressure in the ball, and when it springs back, it pushes right back onto your foot. So if you kick it at just the right moment, you can feel it kind of kick your foot back. So the ball moves in its direction, and the foot moves backwards in its direction. Because I've imparted a force on the ball moves that way, and the force back onto my foot makes my foot kind of rebound that way. You can think of those little balls, tick, 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 those little things that do this, right? Sort of kind of the same thing. Or you can imagine holding one still and it like bounces off like this. So it's the same sort of thing. The reaction force is present because there's always two objects interacting with a force. Now, the important thing that I said verbally that we're going to write down also is that action-reaction pairs of forces, they never cancel. You can never just cancel. It's easy to think that, oh, this one is in this direction and this one is in this direction. They're going to cancel because they're equal and opposite, so there's nothing happening. But that's not true because this force is acting on the ball, but this force is acting on the foot. These forces act on different objects. And so the only way you could cancel something is if you had multiple forces acting like on the same object. But these forces are not like that. In action-reaction pair, they don't act on the same object. They act always on two different objects. So if you're solving a physics problem and you're coming up with an action and a reaction force and you're trying to put them and act on the same body, you've immediately made a mistake because they never act on the same body. Ever, 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 ever. So what I want to do next, I'm going to write one more example under here. And then we're going to write Newton's third law down. Then we're going to draw a bunch of different examples like this. The only way you can really get the feel for action and reaction is to see a bunch of examples. So here is a butterfly flapping its wings. And I already mentioned this one verbally, but let's just do it. Now again, I can't draw, you know this. So this is a wing of a butterfly, and looks like my marker's almost out of ink. Here's another wing of a butterfly. I'll try to clean this up. Use your imagination. That's a butterfly, okay? You have two little antennae like this, right? So you can tell I'm a terrible artist. That's okay. So what you have here is the butterfly doing its thing like this, right? Okay. So what happens is you have a force acting down like this, which is going to be the force of the wing on air. So when you push down, there is a force of you pushing the air down. What would the reaction force be? It would be an upward force, which would be F of the air acting on the wing. I really want you to think about this for a second. The wing is acting on the air is acting on the wing. Notice that these forces can't cancel because they don't act on the same thing. This is a force on the air, and this is a force on the wing. Those forces are acting on totally different objects. So what happens is when you push down, you're pushing and you impart a force on the air. That force moves the air down. But at the moment of that force happening, there is a reaction force where the air is pushing up on your wing. And that is how you kind of maintain your little altitude. Without the reaction force, which actually is acting on your wing, then of course flapping wouldn't do anything. So you're simultaneously pushing the air down while the air is pushing your hand or your wings up. All right, so that is our second little example. Now what we want to do is write down Newton's third law so we can get it on the board before I lose you here. Newton's third law. I encourage you to watch till the end because there's a lot of little examples here I want to get through. So here we go. To every action, and when I say action, it's really an action force. There is an equal and opposite reaction force. You know, I'm not as smart as Isaac Newton. But if I wrote this myself, I would say to every action force, there is an equal and opposite reaction force that act on different objects or on the partner object in the interaction. Because it makes it sound like there's always two forces and they just cancel. Equal and opposite cancel. But that's not what's happening because the forces are acting on totally different things. All right? So there. Now, the way you would mathematically write that is you would basically say some force of object A acting on object B is going to be equal to the negative of the force of object B acting on A. Now we get a little mathematical and a lot of people's brains start to blow up. What does this mean? This means the force of my foot acting on the ball is exactly the same thing as the force acting from the ball acting on my foot. But there's a negative sign here, which just means that it's in the exact opposite direction of whatever the direction of this force was. That's exactly what I've codified here. This force would be like in the positive direction. This force would be in the negative direction. But what this doesn't say, because I'm trying to kind of like beat it into your head so you don't forget it, this equation doesn't, it sort of tells you down here, but it doesn't emphasize that they're acting on totally different objects. So it looks like people see, oh, they're equal and opposite, they cancel somehow, but they don't, because A and B are different objects. Foot and ball are different objects. Wing and air are different objects, and so on. And then the next thing I want to write under here is a note. It's not really part of Newton's law, but it's just as important as everything we've written here. Let's see, these action and reaction forces, action and reaction forces never, now underline with a quadruple underline, never act on the same object. And I will follow that up with saying they never, underline, 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 cancel. So, yes, sometimes in physics forces cancel. Sure, happens a lot. But never an action-reaction pair, ever. Never does, because they act on different objects. And we're going to get to some examples. I'm sure in your mind you're thinking, well, we've already done some examples where I think they cancel. Well, those were not action-reaction pairs. I'll get into the details in just a minute. We'll show you some examples. So let's jump. We've already done two little examples right here. Variety is the spice of life. Let's do a little bit more. Let's talk about a bat and a ball. Right, a bat and a ball. So you're standing at the mound, you crack against the bat, against the ball, and what do you have? You have some bat, which is some elongated object, and you have some ball, which is some spherical object, and of course it's swinging kind of like this direction, and it hits the thing. So at the moment of impact, this ball experiences a force. I'll represent it right here. This is a force of the bat on the ball. This force is what makes the ball go away from you. But at that exact moment, there is an equal and opposite force down here, which is the ball acting on the bat. Now, if you hit it, if the ball and the bat are similar masses and similar construction of materials, and you hit it just right, you can actually see this force acting on the bat and kind of kick the bat backwards, okay? But in baseball, what usually happens is that you follow through with it and you're applying more force in your shoulder so that even though there's a reaction force on the bat, you're overpowering that reaction force with more muscle power in your shoulder. So you don't see the bat bounce back like this, and that's because you literally are following through with additional force from your shoulder, and so you don't see it, but it is there. And if you hit a ball, you can feel the resistance onto the bat at the moment that the bat hits the ball. But notice that these forces one of them is acting on the ball, one of them is acting on the bat. And so because of that, I'm going to write down here, no cancel. I want to drill this in your head. These do not cancel. They're different bodies. These forces are acting on different bodies. No cancel. These forces, the wing acting on the air acting on the wing. No cancel. You see, I'm just going to beat that in your head over and over again because it's so important. You know, you'd be surprised how many times people write that down and they try to cancel it, and it's just obviously not right. All right, let's talk about swimming. Whoops. And instead of swimming, if you'd rather, you can think about canoeing, if you want to think about canoeing. So you're in the water and you're swimming. How do you swim? You put your hand forward, you kind of slide it into the water, and you pull backwards. And then that lunges you forward a little bit, and then you do the whole thing again. So I can't draw swimming. I'm not even going to pretend, right? So here's my little stick figure. I'm looking top down. Here I'm in the water. And just to do a little blow up and show you what's going on, my hand is extended out into a gigantic little hand right there. Or you can think of it as a little flipper on the end of my hand, okay? So what you have going on, all this is water surrounding me, and you're looking top down on me like this. And what happens is I'm exerting a force from my hand on water. And this force pushes the water backwards. You can see the swirlies in the water. That's what's going on right here. What's the reaction force? Well, then the force right here is the water on my hand. Now, it looks like they would cancel right here, but I just can't draw it so cleanly. These do not cancel. Because even though I drew it right here as if it's like, you know, really the better thing to do would be to kind of like separate it down here and then say that the force is really, because the force is really acting on the water in the microscopic layer right by my hand. That's where the force is. I'm acting on the water. And what does that do? That pushes the water back. If you're canoeing and you're doing that, then you're watching the water slide past you, but at the same time, you're watching the boat lunge forward because the water is pushing on you. The force acting on the boat is the force of the water there. But these are not canceling because one of them is acting on my hand and one of them is acting on the water. Two different things. All right, let's talk about a collision. Now, I don't want to talk about collision of a car or anything like that. I'm just saying like two objects. Here's object A here, and here's object B right here. And what's going on is this one's traveling right here with some velocity, and this one's traveling here with some velocity. So obviously they're gonna collide with each other. So 1 or 2 seconds later, these things are going to interact with each other, and they're going to think about two billiard balls or pull balls or soccer balls or whatever, and they hit each other. This is still object A, and this is still object B. So what's going to happen is there's going to be some forces going on right here. So this one is going this way, and this one's going this way. And so what happens is this ball experiences a force in this direction. And this is the ball A acting on the ball B. On ball B. Because of ball A, it has a force acting this direction. And at exactly the same moment, this force is going to be ball B acting on ball A, like this. And these forces are equal and opposite, but they don't cancel. No cancel. Because this force is acting on this ball, and this force is acting on this ball. So what actually happens? They're going to hit each other, boom, and rebound from each other. This force is responsible for making the ball fly this way, and this force is responsible for making the ball fly this way. So these two forces that are happening due to the collision, they're responsible for then the rebounding that's going on in both directions when the balls fly apart. Okay, I do have a couple more before we do our kind of like our bigger problem. Let's talk about the Earth and the Moon. The Earth-Moon system, right? So we have a giant planet, which we call Earth, and we have a smaller planet, satellite, which we call the Moon. All right, now we all know that the Earth attracts the Moon. We all know that. So there is a force right here. This is the force of the Earth on the Moon. This is trying to pull the Moon in. Of course, the Moon is moving sideways, so it's orbiting. We'll get to that later. But there is a force of the Earth acting on the force of the Moon. That's this arrow. What would the reaction force be? It has to be acting on the other body. So there has to be a force on the Earth right here. Force, this is the Moon acting on the Earth. And it's an equal and opposite magnitude force. Now, this is kind of like I'm showing this example because as far as I can tell, this is the only example where the two bodies aren't touching so far. Notice here, the collision, they're touching. The swimming, they're touching. Baseball bat, they're touching. Over here, the butterfly, the air is touching the wing. The ball is touching the foot. Everything's a contact force, but here, there's a separation. But there's still an action-reaction pair. If the Earth pulls on the moon pulls on the Earth, and those forces are the same. So then, you might even take that to its extreme. This marker is being pulled on by the Earth, but that's one force, okay? But then there's another force where this marker is pulling the Earth. They act on different objects. One force is acting on this marker, and the other force is acting on the Earth, and they're equal and opposite. But when I drop this thing, this is such a small body, then of course it moves rapidly. The Earth actually is attracted and falling upward to this at exactly the same time. But since the force is so small, the Earth is just not going to move much. So whenever we drop objects, of course the Earth is attracted and trying to move up as well, but it's just so much more massive, we never notice the Earth kind of rising up there. But when we have two planetary bodies like this, we actually do see that when they orbit, they actually don't orbit. It's not like the Earth is like fixed in space and this thing just goes around. Really, when you have like a binary star or two planets close in mass, they sort of orbit each other. They orbit a common center of mass of the system because they're both attracting each other, okay? We don't notice it with markers in Earth because the marker is so small, it's effectively tiny and insignificant compared to the Earth.
Learn anything at mathandscience.com.